So the example that we have here, number 5, is actually going to be very similar to that example we just looked at last class. It might actually help to kind of start out with, again, a diagram to help us out here. So this example is talking about, again, a sailboat that leaves a pier heading due west at 8 knots. After 15 minutes, the sailboat changes course to north 16 degrees by west or north by northwest at 10 knots. So obviously it's picking up a little speed there. And then they're saying basically find the bearing and the distance from the pier after they have been 12 minutes on this second course, you know, when they change their course. So if you kind of similar, as I said, to the previous example. So let's imagine this is our pier. They're talking about heading due west, right? At 8 knots, I think they said. So that means if this is our boat, it's going to start going out due west for 8 knots, and it stays on this course for 15 minutes. Then they are telling us it changes course and goes basically in a northwest direction at a 16-degree bearing. So that is going to be, and my degrees are obviously not going to be very accurate, but let's say they start going. And remember, bearings are always with respect to a north-south line, right? So if we draw this little dotted line here, basically this angle here has to be our 16-degree angle. And they are going at 10 knots. They're actually asking us to find the bearing and the distance after it has stayed for 12 minutes on this course, which means they're going to be in this direction for 12 minutes. Right? Okay. And then once they get at 12 minutes, they're actually asking us what the bearing and the distance will be from the pier itself. So that's actually going to be the distance we're going to need to find. And again, let me remind you, when they're asking you to find the bearing of the boat with respect to the pier, they are actually going to be asking you for this angle, because the bearing is always going to be with that north-south or vertical line. Okay, so that's the angle we're going to try and find. And I guess I'm going to call this side C. That's the distance we're going to need to find. All right, so the starting point for the pier, I'm going to call that point A. Whoa, what happened? Okay. The point where the boat turns and starts going northwest, I'm going to call that point B. Okay. Where it ends up finally, I'm going to call that point D. And I'm actually going to drop a perpendicular line from that point D going towards B and create a small little triangle over there. And that corner is what I'm actually going to call point C. Okay, and then of course, we are using the traditional north and west direction. Okay, so let's try and fill in some information here. And then of course, we'll need to use our trig functions to come up with some other information. So the first thing we're actually going to need to know is, let's go ahead and calculate what this angle is going to be. Or essentially, we need to calculate this angle here for that smaller triangle BCD. So any ideas on how we can calculate angle B or angle D? 90 minus 16, yeah, because this angle right here, let me see if I can use, because this would again would be a 90-degree angle, wouldn't it? So yeah, you can just do 90 minus 16, and what will that end up giving us? 74, yeah, very good. So this little guy here is going to be 74 degrees, all right, very nice. What about angle D then for a triangle BCD, this guy here? It will actually go back to being 16 because we know all three angles have to add up to 180 degrees. But you can also actually use the idea of, let me make sure I'm saying this correctly. Yeah, it's called the alternate interior angles. I had to actually look that up. So alternate interior angles, so yeah, they're going to be equal. So you could have used that information also. All right, now let's talk about those 8 knots and 10 knots calculation, because we actually need to figure out what those nautical miles are going to be, right? The distance that the boat has actually traveled. So 8 knots is actually the same thing. Is the same thing as 8 nautical miles, but that would be for 1 whole hour, right? Because that's how you calculate knots or nautical miles. But they only traveled for 15 minutes on that path. So what would we need to know? Because they didn't go a total of 8 knots, because that would have been if they had traveled on that path for an hour. They only stayed in that direction for 15 minutes, and then they ended up going northwest from there. So how would we know what distance have they actually traveled? Because 8 knots is their speed, right? Basically how fast the boat was going. So if it's 8 knots in an hour, in 15 minutes, how far did they go? 2, yeah, because that's just 1/4 of the time. So you can actually do a calculation where you are taking 15 out of 60, right? Because again, remember this is trying to think how I want to write this down. I guess just per hour is what that speed was. So you're taking 15 minutes over 60, which would end up giving you 2 nautical miles. So this distance here, okay, is 2 nautical miles. Now do the same thing with the 10 knots that they went in the northwest direction, and what will that give us? How many nautical miles did they travel? Because they did 12 minutes on that path, right? Yeah, 12 minutes on that path. So that would be 12 over 60, right? Yeah. Yeah, it will actually come out to be 2 nautical miles. Very good. This guy is this one here, which is 2 nautical miles. Okay. So far, we are looking really good. Okay, we've got our angles. We've got our distance. So what do you think we should calculate next? C? Are we ready for C yet? I don't think we have enough information. So let's look up at what information you have right now. You have the distance from A to B. You have the distance from B to D. Bless you. And we know, I guess you can say you know all of angle B, because that would be 90 plus 16, right? Which would be that internal angle here for the bigger triangle. But will that be enough information for us to go about calculating? Because we haven't really talked about obtuse triangles that much. So how would you calculate either angle A or angle D for the bigger triangle ABD? What I think, and this is how I did it, was we should actually find out what this distance is here, and we should find out what this distance is here. Because then I can take the bigger triangle, which would be ACD. If I know this distance, I know this distance, then you can basically use one of the different methods of Pythagorean theorem or one of the sine cosine functions to help you out with that. And then of course, that can also lead us into finding the angle. So how would we find those smaller sides? So let's say this guy here would be side D, this guy here would be side B. So just looking at triangle BCD. Tangent of 74. Well, but then tangent is using opposite and adjacent, and both are unknown. But we do know the hypotenuse, right? So yeah, either sine or cosine would work. And I think we're actually going to need both to calculate side B and side D. So let's start with side B first. So if we're trying to find side B, which function would you use? If we're talking side B, which is the opposite side from angle 74, right? So that would be sine. If you're finding side D, then cosine, right? Okay, so go through that and let me see what numbers you're coming up with. So this is with respect to angle B. So that would be sine of angle B, which is opposite over the hypotenuse. Our opposite would be side B, which is unknown. Hypotenuse would be 2 nautical miles, right? So 2. Angle B is 74 degrees. And I'm actually not sure if these give you nice and clean answers or if they're going to be decimal answers. They're decimals? Okay, so you know what? We're just going to leave it as it is because we don't want to mess around with rounding and all of that. Okay, so don't multiply, just let it be. We'll do all the final calculation when we're getting down to our bearing and distance. Same thing for side D. But for side D, we're going to be using the cosine function on angle B. So that's adjacent over hypotenuse. Adjacent is side D. Hypotenuse, again, is 2 nautical miles. Bless you. Bless you. Again, we're kind of doing this more in a general way, right? Because we're not really interested in sides B and D. That's just to help us get to our final answer. So we're going to let those guys be. So B is 2 times sine of 74. And D is 2 times cosine of 74. All right, so at this point, are we ready for what we're actually trying to find? So we've got our distance between C and D. We've got our distance because this distance would be what? The AC. So it's not 8 knots, right? Because it's actually 2 nautical miles plus the 2 cosine of 74 degrees. So that's actually your entire distance for the AC side. Our distance for CD is, of course, 2 times sine of 74. So we should be able to use those. We've got, technically, I actually want to find this angle A, which is for the triangle ACD. So if I want to find this angle, I know these 2 sides, what can I use? Yes, exactly. Because once you know this guy, this angle would be easy to find, wouldn't it? Okay, so let's start with that angle A. So now we're moving on to triangle, which is the bigger one, and that is ACD. And we're trying to find angle A. All right, so that's going to be tangent on angle A, which is opposite over adjacent. Your opposite side is side B. The adjacent side is going to be the side D plus the 2 nautical miles, right? We don't know what angle A is, which is what we're actually trying to find. Our side B calculation was 2 sine of 74 degrees. Side D was 2 cosine of 74 degrees plus those 2 nautical miles for the 8 knots. Now, since we're trying to find angle A, what would we need to do here? Yeah, very nice. Use arctangent, tangent inverse. Yeah, exactly. So that would be A equals tangent inverse or arctangent of this fraction here, basically. This is where you would actually now go ahead and plug this all in your calculator and get a decimal approximation. Adrian, you're looking a little lost to me. Okay, so we're actually trying to find angle A, right, which is that smaller angle. And since we don't know that, what we do have, let me get back to our image here. So we're trying to find this little angle right now. I have this entire side. I know the distance. We know this little guy D here is 2 times cosine 74. And we calculated this distance from A to B as 2 nautical miles. We also have this distance, which is 274, sine of 74. So now ignore this middle part. You're looking at this bigger triangle, ACD. So this is going to be, with respect to angle A, this is our adjacent side. This would be the opposite side. And since this is your 90 degree, this is our hypotenuse, right? So right now, to calculate this function, since I know opposite and adjacent, that's a tangent function, isn't it? So that's why we're using tangent. But to find this angle, you can't have an unknown tangent of A, because what would you put in here if you were going to calculate? So to get rid of the tangent, you use the tangent inverse. Remember how we were talking about what tangent will do, tangent inverse will undo? So that's why to undo this tangent function, we have to use the inverse tangent. Okay, and then you're going to do it on this same fraction of opposite over adjacent. So be careful. Parentheses are going to be your friends here. So when you are typing this in, of course, we're doing the tangent inverse function. For the numerator, the entire numerator, I would put in one set of parentheses. So I don't know if your calculator by default opens a parentheses or not, but mine does. So it's actually going to end up looking like this on our calculator. You've got tangent inverse, open parentheses. I'm going to open another one. Do 2 times sine of 74. Divide. So that should actually be, because sine opens up its own parentheses. So that's 74 close to, divide by, open parentheses again, and this is if you want to try and do it all in one step. 2 cosine of 74 I'm going to try and actually see if this works. I'm not sure if it will. Plus 2. Okay. So if you're being careful with those parentheses, let me see what answers each one of you came up with. Even or rounded?
Even.
Even?
Yeah.
Okay. Did you get? You should have looked.
I did not get that.
Okay, so did you try to type it all in at one go?
Yeah, but
Let me
is
see.
it radians or degrees?
It should be degrees.
Oh.
You're
I
in
thought it
radians.
was in radians. But
No, because
I seen
you're-
a degree.
Yeah, 74.
Yeah, I know.
You're still not getting exact degree now. So let me see what you typed in there. You put disposing inverse of them. 2 times sine of 74. Divide. 2 times cosine of 74 plus 2. Okay, close your parentheses now. Then, so I think we're going to need more than that. So tangent inverse. Already opening one parenthesis, open another one. Then do 2 of sine 74. If there's a division of sine also opens up parentheses.
Double parentheses.
Then do double parentheses. Then divide. Open parentheses again. 2 cosine 74. So we're just closing 74, right? No, 2 plus 2.
Plus 2.
Then 2. Alright, let's try that. Yeah, so it's just because we want the tangent inverse function to know that this entire thing is going under tangent inverse. All right, so angle A is coming out to be 37 degrees. Now remember, that's that little guy here. If he is 37 degrees, what is our bearing angle going to be? 53 degrees. Yeah, very good, because you're going to have to do for the bearing angle. Just 90 minus, right? Because again, this little corner here with the pier is going to make a 90-degree angle. So you're just doing 90 minus the 37 to get your 53. So remember, 53 is the actual answer we're looking for. 37 just helps us get there. We still have to talk about the distance A to D, or that line AD. So how are we going to find that? Oh, and one more thing. Since we're talking about bearing, what direction is that 53 angle in with respect to the pier? Northwest, yeah. So you're actually going to write your bearing, whoa, as north, 53 degrees going west. Okay, now back to the distance AD. What are you going to do for it? You know, with all those 2 sine 74 and 2 cosine 74 plus 2, you can try it. I honestly did not try it with the Pythagorean theorem. So I would say try it and see how it goes if it gets too messy. Because I actually just fell back and used, since we're trying to find the hypotenuse of the bigger triangle ACD, you can actually use sine or cosine on that 37-degree angle and go from there. And I actually use sine, so I wouldn't have to do that plus 2 for the longer adjacent side. But if anybody's trying Pythagorean, let me see what you come up with. Okay, so we're still doing the bigger triangle ACD. And like I said, the way I did it was using the sine function on angle A, using opposite over hypotenuse, which would be the side B over side C. We know that little angle A is 37 degrees. Side B is 2 times sine of 74 degrees. And we're trying to find side C. What method did you use? With the sine, okay.
It's Pythagorean.
You did Pythagorean, okay. And what answer are you coming up with?
3.194.
Okay, very good. What method did you use?
I was going to try use.
You're going to try the sine? Okay, what about you two? What function?
I did
Pythagorean?
like 1945.
Okay, I'm glad that the Pythagorean is working out then, because yeah, honestly, I just chickened out and I didn't want to use that big calculation, but I am really glad that the Pythagorean is also working out. So this guy here, with my method, as you can see, we'll need to multiply both sides by c, so we can get c by itself, and then divide by sine of 37 degrees. That should end up giving us c equals 2 sine of 74 degrees divided by sine of 37. So again, if you're typing this at one time in your calculator, just make sure you're putting parentheses around the numerator and denominator. That should be 2 times sine of 74 divided by sine of 37. And your raw answer guess we'll do, I'm not sure, maybe 1 decimal place. And since we're talking in terms of distance, what will be our unit here? Yeah. Nautical miles, so 3.2 nautical miles from the pier at a bearing of 53 degrees north by northwest. It's a pretty long-winded process, right? I mean, you start by finding either one of those angles to help you out from the smaller triangle BCD, find the sides B and D, and then using those, you come back to the bigger triangle ACD, and then try to find what that smaller angle A will be. Subtract that from 90 degrees to get your bearing angle itself, and then of course using Pythagorean theorem or one of the trig functions to help you come up with the distance of the boat from the pier. And there is a very good chance you will see something like this on the exam. So if you're not sure about any part of this, any confusion, you should ask me that now. Because like I said, it's got multiple steps involved in it, right? Is everything looking okay for now? Yeah? Okay. Alrighty, let's go back to our handout. So the last part that we actually want to talk about here is the harmonic motion. Now again, I think most of you said you had a trig class before, so that's something you guys must have studied, right? So when we're talking about harmonic motion, you're basically talking about, you know, when a point on your object will vibrate, oscillate, or rotate. Sometimes they can also think about it as a point that moves in that wave motion. So in this case, we're actually talking about a ball, and you can kind of see the image on the next page here. So we're talking about this ball basically moving up and down or bobbing up and down at the end of a spring. And so they're talking about the maximum distance that the ball will move vertically upward and downward from its position of rest. So that position of rest where the spring hasn't basically been pulled, right, is going to be your equilibrium point. And so they're saying in this example, we're talking about a movement of 10 centimeters. So it can go downwards by 10 centimeters or go up by 10 centimeters. They're saying basically the time it's going to take for the ball to go from its maximum displacement above zero to maximum displacement before zero or below zero and getting back to its equilibrium position is going to be a total of 4 seconds. It's going to take 4 seconds for that ball to go in both directions and then come back to its original position. So they're saying as long as you have good ideal conditions, perfect elasticity, there's no friction, there's no air resistance, the ball obviously should keep moving up and down in that uniform and regular way. And I mean, if you did want air resistance and friction and all of that, you're probably going to set it up in an experiment, not just regular, because it's going to start slowing down after a while. But the idea is if we were able to maintain that ideal condition, it should keep in that motion. So you can kind of see when we're talking about below zero, you're actually looking at the negative side of your calculation or negative movement. And then of course, if you're above zero, you're at positive 10. So below is negative, above is your positive. So that period, the time that it takes for that entire motion to complete, to go from the starting position to minimum, maximum, and back is 4 seconds. So we're calling that our period. How far does the ball get displaced from its original position? 10 centimeters is going to be the amplitude. And again, you can see these are the same terminologies that we were using when we were describing our sine, cosine functions. Now they are also talking about frequency, and that's 1/4 cycle per second. So can you tell me where they came up with that 1/4 value from? So you can see we're describing the frequency as the number of cycles per second. It's taking us for the entire motion to complete 4 seconds, right? The entire period of this movement is 4 seconds. So if in 4 seconds you're getting the entire movement done, in 1/4 of that second, or one of those seconds, you will only get 1/4 of that cycle completed, right? So that's actually where that 1/4 is coming from. So basically they're saying any motion that can be described by this nature can be described using your sine or cosine function. And that's what we're calling as our simple harmonic motion. So again, just your formal definition here, a point that moves on a coordinate line is in a simple harmonic motion when its distance d from the origin at time t can be given by one of these functions. So d equals a times sine of omega t, or d equals a times cosine of omega t. Of course, your a and omega are going to be real numbers. Omega is always going to be a positive value, greater than 0. Remember, we always talk about amplitude as a positive value again. So even though you're looking at that negative 10 centimeter displacement, the a value would still be absolute value. So that's going to be a positive. Period is going to be 2 pi over omega. Is this looking familiar to you? Normally, instead of omega, what do we use there? Not C. B. Yeah, so what they're actually doing is just replacing that B variable for the which helps us come up with the period with the omega. So this would have been bt. T, of course, is replacing your variable x with time t. And then if you would have had that minus c, this would be exactly like what we were doing, what was it, 1.5, 1.6 section that we talked about it. So that's exactly what your calculations are still the same. And then, of course, your frequency is going to be the reciprocal of your period, which is omega over 2 pi. Okay, so just as an example here for that same ball that you have above, they're talking about the spring is at equilibrium, which means you haven't moved the spring, your distance is 0, and your time is of course 0 because you're at the starting point. So if you have that, and we're using the sine function here, we know we have a maximum displacement of 10 centimeters, so that's going to be a value or amplitude of 10. They're telling us the period is 4. So remember, that's the period, not the omega value. You have to calculate the omega based on this 2 pi over omega. So same thing, you're basically going to interchange the places of 4 and omega. 2 pi divided by 4 will give you pi halves. And then once you have your a and omega values, you can again put it back into that standard form of the equation and come up with what the equation should be. They're talking about a will be positive or negative 10, depending on how your ball moves up or down. So I think we're actually doing the same kind of calculation. They're just changing up our amplitude and period here. Okay, so let's take a look here. Write the equation for simple harmonic. When d equals 0, when t equals 0, the amplitude is 6 centimeters and the period is 3 seconds. Okay, so this guy is, again, starting out with our general sine format equation here. So this is when d equals 0 and t equals 0. You could actually also use the cosine function here, so it doesn't always have to be sine. You can do sine or cosine. Okay, they're telling us the amplitude is 6 seconds, period, sorry, 6 centimeters in 3 seconds. I think I said that backwards. And that's going to be 2 pi over omega, right? So what does omega come out to be? Yeah. So basically you're multiplying both sides by omega, dividing both sides by 3. Okay, so what's your equation going to look like? Very nice. And if instead of sine, this guy was cosine, what would be the difference here? No, negative is just if you're moving below 0 or above 0. So that wouldn't make a difference. So honestly, what would be the difference between the sine and cosine function then? Just the starting, yeah. But equation-wise, literally you would be replacing sine with the cosine function, right? Because the amplitude and the omega values would still stay the same. So yeah, just kind of keep that in mind. Yes, ma'am. No, it really wouldn't. Because that, like we were saying, is just going to be, because remember how sine starts at the intercept, if you're just thinking in terms of the graph, and the cosine starts at the maximum value, that would be the only difference. Alrighty, very good. Okay. So that was just kind of coming up with a basic equation here. Now they're talking about where else you can kind of think about this harmonic motion. So they're talking about here the relationship between sine waves and the harmonic motion in the wave motion. So they're talking about, think about, you know, what happens if you drop a little stone in a pool of water. You see that rippling effect, right? The moment that stone hits the water, it's going to start rippling outward. So they're kind of thinking about, you can think of that as being the shape of the sine or even the cosine function. So they're saying now, after you've dropped that stone and that rippling effect is happening, think about if you drop a fishing bobber, or you're basically trying to fish in that same rippling water, that fishing bobber is not going to go horizontally, right? Because those ripples are going to make that bobber go up and down. So basically that's what they're kind of thinking about in terms of what that simple harmonic motion would end up looking like. So either think about that spring being pulled up and down, or you can think about this example here with the bobber moving up and down. Okay. So now they're actually giving you the equation. They're saying you have d equals 6 times cosine of 3 pi over 4 t. Did you have a question?
How can I read that?
Oh, I actually did not notice that till after I printed your handout out. So I do apologize. I didn't realize. Oh, and that one doesn't even show up, does it? Yeah, because I was looking through my notes before I came to class and I was like, ooh, I can't read that. I'm sure none of you can read that either because that was with glasses on. I still couldn't read it. Let me see if I can pull something. Wow, that really does not show up. This is, yeah, thank you. All right, let me see if our textbook will be any helpful. Sometimes it is, sometimes it's not. This guy is 1.8. You can read C?
Yeah.
Okay, well, you guys are definitely better at than me then, because I am not really seeing C that clearly. I think that's a 6, since we know it's a 6 at the amplitude value. Okay. There we go. Are you gonna show me? Oh, and that's something I did want to mention. They do have like videos and stuff in your textbook if you guys ever want to go. You know, I think your textbook is the culprit because look at that.
Oh, but we can read it there.
You can read it there. So I'll go ahead and write it down on your handout because this is really terrible. Okay, so you've got frequency equals omega over 2 pi. And then omega we know from the function is 3 pi over 4. So it's 3 pi over 4 on the numerator divided by 2 pi. And then you basically end up with 3 over 8 as your cycle per unit of time. So 3 over 8 cycle per unit of time. And again, if you just want to verify that part C. Alrighty. Okay, you know what? We'll just do the example from here. So they're asking us to figure out, once you have the equation, 6 times cosine of 3 pi over 4 t, what the maximum displacement is. Now, of course, we know the maximum displacement comes from the amplitude, right? So that's going to be 6 units. And then we know it's going to be positive 6. If you are above 0, it's negative 6 if you are below 0. Okay, the frequency was the part B calculation. So remember, frequency is the reciprocal of the period. So it's omega over 2 pi. Your omega value is coming from the coefficient of t. So we know 3 pi over 4 is the omega. So you're going to have 3 pi over 4 divided by 2 pi. So basically what's happening here is the pi and the pi cancel out. The denominator of 4, you end up multiplying with 2, which is where that 8 is coming from. So you're ending up with 3 over 8 cycles per unit of time. And I guess they haven't really specified if we're looking at this in seconds or not. So we cannot specifically say if it's minutes or seconds. So you're just leaving it as unit of time. Now they want to know what the value of D will be when we substitute in T equals 4. So obviously you can see that calculation is going to be where the 4 and the 4 will end up canceling each other out. You're going to be left with cosine of 3 pi. Now think in terms of the unit circle. Where does 3 pi fall on our unit circle? Is it at the starting point of 0, 0? Because that's 0. And then once you make a circle, no. Yeah, because you got to figure out in terms of unit circle where you're going to be at, which is in degrees. 180, yeah, because remember you start at 0, you make a full circle, you're at 2 pi when you come back to the starting point. This is pi, right? So
Yeah.
I was going to say upstairs. The value at the above point is going to be pi halves. The bottom one is 3 pi halves, right? So your whole pi is going to be at the 0 and the 180 degree. Yeah, so that means 3 pi, you're actually going to be coming back at 180 degrees, which is -1. So that's where they're getting that -1 value from, and then 6 times -1 is at -6. So if you're at a distance of -6, where are you at in terms of that harmonic motion? You're going to be at the bottom because you're below 0, right? I mean, think in terms of that spring, if you will. Now the part D here is asking you about the least possible value of t for which your distance will be 0. So what can that least possible value be? So that actually means, yeah, you're basically working backwards to find what that t is going to be. So you're starting out with your 6 cosine 3 pi over 4t equals 0. Of course, you're trying to isolate that t variable. So the first thing we do is divide both sides by 6. 0 divided by 6 is 0. And then the idea is for the equation cosine 3 pi over 4 times t equals 0, they're saying basically 3 pi over 4t is going to be satisfied when it is equal to, no, not this guy, pi halves, 3 pi halves, 5 pi halves. So where are they getting that from? Okay, I actually need to bring this guy down. So think about where is your cosine function equal to 0 at? Back to the unit circle. Yeah, at 90 degrees and 270 degrees, right? So the above and the below point on your unit circle on the y-axis is where my cosine is 0. So we know it's going to be basically multiples of pi halves. So you're going to have pi halves, 3 pi halves, 5 pi halves. You basically keep going in that 180 difference or pi halves difference. So the idea here is where the cosine function is 0, you can work backwards from there. And then you're basically taking this, inverting it and multiplying it on the right-hand side. So you're multiplying by 4 divided by 3 pi, and then whatever these guys clean up into will be what your t value is going to be. And then they're talking about the least possible value. So it's going to be that first one, yeah, 2/3, because then the numbers are getting larger from there. So your least value should be at 2/3. So this part here, all you are doing, and let me see if it will let me do a little annotation here. Okay, so we've got okay. This, and so if you have 3 pi over 4t equals pi halves, 3 pi halves, and all of that list. So basically to figure out what t is going to be, we multiply both sides by that inverse of 4 over 3 pi. So these guys will cancel out, leaving you with t, right? You're going to be doing pi halves multiplied with 4 over 3 pi. Same thing for 3 pi halves multiplied with 4 over 3 pi. So basically, your pi will cancel out, right? 2 goes into 4 twice, and you will be left with 2 on the top, 3 on the bottom. So that's where they got that 2/3 from. On this side with the 3 pi halves, 3 pi and 3 pi will cancel out, 4 and 2 reduce down to a 2. So that's how they're getting that value. So it's basically just starting out with where cosine is going to be 0 and then working your way down from there. The least value, exactly, yeah. So the first one is the only number we're interested in, and then you ignore, I guess, the rest of them. Okay, let's save that. I think that's pretty much it. Oh, guess I should clear you out. Come on. Okay, so you are actually looking at a similar example here, but we're given d equals 4 times cosine of 6 pi over t. So you're still answering parts A, B, C, and D that you did in example 7. So what are we going to have as our maximum displacement here? Because that's coming from your amplitude, right? So okay. Can you tell me what the frequency will be for this guy? The frequency is omega over 2 pi. Omega is very good. That's going to be that coefficient on the t variable. Pi and pi will cancel out. 2 goes into 6 3 times. And that's going to be cycle per unit of time. Again, we don't know what unit of time they are using. Alrighty, we'll actually pick up with parts C and D next time. Let's give you guys enough time to go through the quiz. But that's pretty much it. I mean, as soon as we're done with this example, we're done with 1.8.